Name, please.
Gio.
Wait one moment. Let me just look through these 10,000 other names to find your name. Oh, for goodness sake. Let me go back to the beginning again. What's your name again?
Oh, come on, mate, hurry up.
Yeah, it's whatever, you can just go in.
Hey, mate, what's your private key? Don't use a key store?
Seems like I should be using Merkle trees.
The problem. How do I verify that some data is in a group of data? And as this example demonstrates, let's say I have a list of names that are VIPs to some club. How do I determine if someone's name is in that list in an efficient and verifiable way? Another example of this is airdrops. An airdrop is where some tokens are issued to multiple addresses, usually for free. And so in an airdrop, you need a list of addresses that are eligible for these free tokens. How do I determine if my address is eligible for the airdrop? Now you may be thinking I could have an array or mapping of addresses in Solidity, and I could just loop through this array of addresses, and I could just check if my address matches one of the addresses in this array. But this can be extremely challenging. Imagine if this list is extremely long, thousands of names or addresses long. As the list of names or array of addresses grows, looping through this array is going to become extremely costly. And at some point, a denial of service is going to occur, in which a name or address cannot be checked due to insufficient gas. So instead, we use a data structure known as a Merkle tree. Now, you may have heard the word Merkle before in terms of Merkle trees, Merkle proofs, Merkle roots. But what are these things and what does it even mean? Let's go through this now. Quick history lesson. Merkle trees were invented by Ralph Merkle. Ralph Merkle was a computer scientist and mathematician and also one of the inventors of public key cryptography. And he invented Merkle trees in 1979. So as I said previously, Merkle trees are a data structure, and Merkle proofs are a way to prove that some data is present in this Merkle tree. But we still don't actually know what this data structure is. What is a Merkle tree? So imagine a tree, and now turn it upside down. So at the bottom, you now have the leaves, and at the top, you have the root. And this is the same with Merkle tree data structures. Each of these leaves in the tree is a piece of data, and then the branches and the root are built by hashing different pieces of data together. This is what a Merkle tree data structure looks like. And at the bottom is the leaves, and each leaf represents a piece of data in our Merkle tree. The root is then at the top, and the root is built by hashing adjacent pieces of data together. Now, this may sound a little bit confusing, but by the end of this video, you should be able to understand what this data structure actually means, how we calculate the root hash, and how we prove that some data is present. So each of the leaves represents a piece of data that's present in our Merkle tree. And this is often referred to as a leaf node. And it's produced by hashing some data, e.g. the string of the name Ciara. So at the bottom, I've got my VIP names, Ciara, Sarah, Bob, and Dylan. To produce the leaf nodes, I would then hash each of these pieces of data, for example, using the keccak 256 hashing function to produce hash 1, hash 2, hash 3, and hash 4, by hashing each of these individual pieces of data. Adjacent nodes, such as hash 1 and hash 2, are then hashed together to produce intermediate nodes. So hash 1 and hash 2 are hashed together to produce hash 1, 2. Hash 3 and hash 4 are then hashed to produce hash 3, 4. These two intermediate nodes are then hashed together to produce the root hash. This may sound a little bit complicated right now, but we're going to go through this again in more detail and how this actually works in practice. Merkle proofs are then used to prove that some data is present in the group of data in the Merkle tree. And this data can be literally anything. So here we have the names of people in a VIP club, or they could be addresses for an airdrop, or they could be transaction data. But the leaf nodes are just any hash data. So to summarize, what is a Merkle tree? So it's actually a type of binary tree where each leaf node represents a hash of some data, and each intermediate node is a hash of its two child nodes, and the topmost node is known as the Merkle root. Let's dig into how this works in more detail and go through this again so we can really solidify the knowledge. So first of all, we have an individual piece of data. For example, the string of the name Ciara. Again, this data can be anything. For example, data 1, which is equal to the name Ciara, is hashed to produce a leaf node hash. In Solidity, we would do a keccak 256 of the name Ciara as a string. And this produces hash 1. And this is equal to OX7C0374, blah, 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 blah. And this is the leaf node hash. We then do that with all of the data in the Merkle tree. So we hash the names Ciara, Sarah, Bob, and Dylan to produce hash 1, hash 2, hash 3, and hash 4. Next, we need to hash the adjacent leaf nodes together to produce the intermediate nodes. So we produce hash 1, 2 by hashing together the hash of the name Ciara and the hash of the name Sarah. We hash together hash 1 and hash 2 to produce another hash. So in Solidity, we would ABI encode hash 1 and hash 2 together, and then we would hash that using KERCAC256. And this would produce hash 1, 2. We would then do that again with hash 3 and hash 4 to produce hash 3, 4 in the same way. Finally, we hash together those two intermediate nodes. So we hash together hash 1, 2 with hash 3, 4 to produce a root hash. And again, we do this by, in Solidity, ABI encoding together hash 1, 2 and hash 3, 4, and then hashing that using KERCAC256. And this produces a root hash such as OX6E10 blah 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 for my list of names. Putting this together, we produce the following Merkle tree. But how do we prove that some data is in the Merkle tree? So how do we prove that my name, Ciara, is part of the VIP club? To prove, e.g. the person entering the club or some address is present in the Merkle tree, you need to provide the data, for example, my name, Ciara, and an array of the intermediate nodes required to reconstruct the tree and calculate a root hash. And this is known as the Merkle proof. So, to prove that my name, Ciara, is in the tree, I would need to provide an array of hash 2 and hash 3, 4. So hash 2 is my proof 1, and hash 3, 4 is my proof 2. And my proof is simply an array of these two hashes. I would then reconstruct the tree by hashing proof 1 or hash 2 with the hash of my name. That resulting hash would then be hashed with proof 2 to produce a calculated root hash. This is then compared with an expected root hash to check whether the name is in the tree. This expected root hash would be known by the club owner because they would have all of the names in the Merkle tree. They would then construct a Merkle tree and have an expected root hash, which they could compare with some calculated root hashes by people trying to prove that they are in the Merkle tree. So essentially, this Merkle tree is constructed multiple times. It's constructed once by, for example, the owner of the club to construct the Merkle tree with all of the names in the VIP list and then calculate an expected root hash. Every time someone wants to prove that they are in this Merkle tree, they would have to calculate a calculated root hash using their proofs and the hash of their data, which they could then compare with the expected root hash known by the VIP club owner. Now, because we're using a secure hash function like KERCAC256, it makes it practically impossible to have a hash collision where two different inputs produce the same hashes. Therefore, we can be sure that if we produce a matching root hash in the Merkle proof, you know that data really must have been present and part of the original root hash calculation. Now, this sounds super complicated and a little bit theoretical. Let's look at our VIP example in JSON so we can actually see the Merkle tree in practice. So here you can see the inputs to our Merkle tree. These are the strings of the names in the VIP list. We then have an array of proofs, and these are those two intermediate nodes required to reconstruct the tree. We then have the root, and this is that expected root hash, which we would compare with a calculated root hash when trying to prove that some name is in the Merkle tree. We then have leaf, and this is the hash of the data. So KERCAC256 of the string Ciara. And we have this for each of the leaf nodes, so Ciara, Sarah, Bob, and Dylan. But how do I actually produce this Merkle tree and produce the Merkle proofs? There are two main libraries that are usually used to produce Merkle trees, and that is OpenZeppelin's JavaScript library and DMFXYZ's Merkle Solidity library. And what these libraries do is they take the data as input, they hash all of the intermediate nodes together to produce a root hash. They then write this expected root hash along with all the proofs and all of the leaf nodes together into an output file, such as the one that we just saw for the VIP list. That JSON file was produced using DMFXYZ's Merkle library, which is a Solidity script. I will leave links down below for these two libraries if you would like to look into how they work, but let's go into how we can implement this into a smart contract. To implement Merkle trees into a smart contract to verify that some data is in a Merkle tree, we can use OpenZeppelin's Merkle-proof.sol smart contract. Let's click into this smart contract and see how it works. So we will be using this verify function to verify that some leaf that we provide is present in the Merkle tree using the proof and the expected root hash. So verify takes the proof, the Merkle root, and the leaf that we want to verify. Typically, the root will be stored in the smart contract itself, and the proof will be calculated off-chain using those libraries that we mentioned before, and then the proof is then passed as an argument to this function call. This then calls process proof. Process proof then iterates through each element in the proof array. So we start with the leaf node, and each time we iterate through the proof array, the computed hash is updated by hashing it with the next element in the proof. So we first hash together the leaf node with the first element of the proof, and then the output of that is then hashed with the second element in the proof. If we look inside hash pair, we can see that when hashing both hashes together, we will always take the smaller value first. Efficient hash does the actual hashing. This uses assembly. And this is just an efficient implementation of ABI encoding A and B together and then doing a KCAC 256 on that, because it just doesn't allocate or expand memory. But you can just think of it as the same thing, but just slightly more efficient. If we jump back up to process proof, finally we'll compute a computed root hash, which we will return to verify, and verify will check whether that calculated root hash matches the expected root hash from the smart contract. Let's look at this smart contract, which uses Merkle proof from OpenZeppelin to verify if a name is present in a VIP club. So this function, verify if in club, takes the string name and a bytes 32 array of the proofs. We then calculate the leaf hash, and notice here that we are hashing the value twice. This is important. We'll go through this in a second, why we want to be doing this. We then have an if statement that uses the verify function on the Merkle proof from OpenZeppelin smart contract, passes in the proof, the root which we stored in the smart contract by passing it through to the constructor. So if we have the owner of the VIP club, they would be deploying the smart contract and passing in their expected root hash to the constructor. We then pass in the calculated leaf node to the verify function call. And then if that leaf node is not present in the Merkle tree, the calculated root hash did not match the expected root hash, then we'll revert with this custom error, minimal Merkle not in club. Otherwise, we'll return true, and they are present in the VIP club. That name was present in the Merkle tree. Now let's go back. Why did we hash the data twice? We hashed this data twice because of what is known as a second preimage attack. A second preimage attack is where an intermediate node is presented as a leaf node and therefore passes the check since that intermediate node is present in the Merkle tree. In a second preimage attack, an intermediate node is represented as a leaf node and therefore passes the checks since it is present in the Merkle tree. Now, if we go back to our Merkle tree diagram, you can see here, if we pass in some second preimage attack data, which would be the ABI encoded #1 and #2, so prior to hashing, if we provided that as input to our smart contract, for instance, to the verify function, this would then be hashed to produce #1, We could then provide #34 as the proof, which would then be hashed together with our hash data to produce the correct expected root hash, and it would pass all the checks, even though this data wasn't actually present as an actual leaf node in our Merkle tree. This attack is only possible if the function accepts 64-byte leaves as input, and this is because this ABI encode packed #1 and #2, the two leaf node hashes together ABI encoded, will be a 64-byte piece of data. So if, for instance, this leaf node data that the function accepted as input needed to be 64 bytes long for some reason, then this smart contract could be vulnerable to a second preimage attack. This would mean that the attacker could pass two leaf node hashes encoded together as the input, so before they're hashing. And since in Solidity, hashes are 32 bytes long, the result of encoding the two leaf node hashes together will be 64 bytes long. So you can see in this function, verify bad, we accept arbitrary bytes data as input. We then hash that to produce the leaf node. So we could pass in the ABI encode packed of #1 and #2 as the data, which would be 64 bytes long, since #1 and #2 are 32 bytes long. And this function would be susceptible to a second preimage attack. Now, the first way to avoid this would be to avoid accepting leaf node data that is 64 bytes long. But if for some reason your protocol needs to accept 64 bytes long leaf nodes as the data, there is a second way of preventing second preimage attacks, which actually is just used in all circumstances. That is, as we pointed out before, the fact that we hash the data twice. This is analogous to using a different hash function for hashing the leaf nodes versus hashing the adjacent nodes together. If a different hash function is used or the data is hashed twice when hashing the data to produce the leaf nodes, as when the adjacent nodes are hashed together, we therefore cannot pass two leaf node hashes encoded together as input because the incorrect hash function will be used and the calculated root hash will not match the expected root hash. So if we look back at our Merkle tree diagram, you can see here that the data to the Merkle tree is hashed twice. Got a Keccak 256 and then another Keccak 256. If we passed in the ABI encoded hash 1 and hash 2 as input, this would be hashed twice, when in fact it should be only hashed once. Just note here that even though you're seeing Keccak 256 multiple times in this little snippet, when we actually hash, for instance, hash 3 with hash 4, we are only using Keccak 256 once. Those other instances of Keccak 256 that you're seeing here are when we hash that original data. So if we were hashing this twice, you would actually see 4 instances of Keccak 256, one for each piece of data that was hashed, and then twice for hashing those two hashes together. Since the output of the hash will be different than what is expected, and hash 1, 2 will be different, since it's hashed twice rather than only once, this hash will be different, and therefore the calculated root hash will not match the expected root hash, and the system will not be susceptible to a second preimage attack. By using the two scripts we mentioned earlier to produce our Merkle trees, these resultant Merkle trees were resistant to preimage attacks since the data to produce these leaf nodes was hashed twice. So if we look in the DMFXYZ Merkle repo, and we look in merkle.s.sol, which is the script that can be used to generate Merkle trees, and we scroll down to the bottom, we can see that when we are calculating the leaf node data, we take the data and we hash it twice. So any tree that is produced using the merkle.s.sol script from Merkle or the JavaScript script from OpenZeppelin, both of these resultant Merkle trees will be resistant to second preimage attacks. For more information on second preimage attacks, I will leave a link to a fantastic article by Rare Skills on second preimage attacks if you would like to understand more. So when would you use Merkle trees? There are a couple of real-world use cases. The first one, which we've already spoken about, is in airdrops. Merkle trees are used in efficient airdropping to securely and verifiably distribute tokens to a large number of recipients without needing to store a giant list on-chain. In this process, the list of eligible recipients and their respective allocated amounts are hashed together to create these leaf nodes in the Merkle tree. The root of this Merkle tree is then published on-chain in the airdrop smart contract. Each recipient can then claim their tokens by providing a Merkle proof that is calculated off-chain using one of those scripts from the libraries we discussed earlier. Another use case is in blockchains. In blockchains, the block headers contain information about the block itself, and they contain the following fields: the transaction root, the receipt root, and the state root. And these are those Merkle root hashes for the transaction tree, the receipt tree, and the state tree. And these roots are essentially Merkle roots. Well, actually, they're Merkle Patricia roots. And Merkle Patricia trees are very similar to Merkle trees, where the root hash is dependent on those child nodes. And if any of the child nodes change, the root hash will also change. Again, I will leave some information down below on Merkle Patricia trees if you are interested. And finally, Merkle trees are used in rollups. Rollups are a layer 2 scaling solution that increase the throughput of a layer 1 without increasing gas costs. And in rollups, multiple transactions are bundled together to produce a batch of transactions. The root hash of this batch is then posted on chain. So each of the transactions in this batch represents a leaf node of a Merkle tree. Merkle trees are used in multiple places in rollups, including batch roots, as we just discussed, where transactions are bundled and encoded together into a single root hash using a Merkle tree, and the batch root comprises all transactions in the batch. To prove that some transaction was included in the batch, the transaction details, the batch root, and the Merkle proof showing that inclusion path is provided. Another place is state roots. So the roll-up's pre and post state changes, the state before and after they were included, they are both represented as Merkle trees, known as the state trees. And then these state roots are submitted to the layer 1 chain. And then Merkle proofs can be used to verify some state and prove its inclusion in the rollup. So now, hopefully you understand what Merkle trees, Merkle proofs, and Merkle roots are, when you should be using them, why you should use them, how to use them in smart contracts, and how to create them. To summarize, Merkle trees are just a data structure where adjacent nodes are hashed together iteratively to produce a root hash. A Merkle proof is a way to prove that some data is present in this Merkle tree, and is an array of the intermediate nodes required to reconstruct the Merkle tree. And the Merkle root is just the topmost node in the Merkle tree that we can use to compare a calculated root hash with an expected root hash to determine whether some data was present in the tree. And that is everything you need to know about Merkle trees, Merkle proofs, and Merkle roots.